Sorry, I have a bunch of screens popping up here, but it should work. Okay, so thank you very much for the nice introduction. So I'm Mattia Walschaers from the Laboratoire Cassel-Bruxelles in Paris. As you can see from these slides, I'm working in an experimental quantum optics group. So the two people you see in the background are my two other permanent colleagues in the group. You have Nicolas here and Valentina here, and like good experimental physics professors, they are pretending to do experiments. So I'm the theoretician of the bunch, and I'm going to talk to you about some of the theory work that we have been doing in our group, and which will hopefully maybe one day have some kind of incarnation on this optical table. So when I talk about we, us, and so on, okay, so I'm just going to do it. For some reason my slides do not want to change. Yes, okay. So when I talk about us, I talk about the multi-mode quantum optics group. So this is the bunch of people that I'm working with. So the work that I will present you today is theory work, so it's mainly done, most of the people here are experimentalists. So the work is mainly done by Mathieu and Carlos, who are the little theory group that we have, and our long-term visitor, Xiaoting, who visited us for 1 year from Beijing. And so the relevant collaborators here are Ulysse Chabot from INRIA, who is right next door, and Xiong Yihe, who is in Beijing, the other side of the planet, basically. So we do continuous variable quantum optics. Given the diversity of the community here, I decided to give a quick introduction. So it will not be a big surprise to you that we study light, electromagnetic fields. And so we do continuous variable quantum optics, which means that the observables that we are interested in are essentially the amplitude and the phase of the electric field. So we like to represent these quantities on something known as the optical phase space. You can think of this representation as basically you take a vector, the length of this vector represents the amplitude of the field, and then the angle here represents the phase with respect to some kind of reference. And usually it's more convenient then to actually describe things in terms of the values along these two axes that I labeled Q and P. So these axes are what you call field quadratures. And field quadratures are important because they are actually things that you can observe. You can use a thing called a homodyne detector that will actually measure a value along this axis and a value along this axis. Why do I call them Q and P? Well, the reason is kind of simple. I want to give you a bit suggestive because these observables, they follow the canonical commutation relation, which means that they behave essentially as position and momentum operators. Of course, me as a theorist, when I see two operators that do not commute, I'm going to tell people that you cannot measure them simultaneously at the same time. When you tell an experimentalist that they cannot measure something, they will of course try to measure it. And so you can do these kind of things where you do, so this is, we call this a double homodyne detection. Some people prefer to call this heterodyne detection. And so the idea is that you take your signal of interest, so this would be our light that goes in, you split it in two on a beam splitter, you send one half to one homodyne detector that you configure to measure along one axis, you send the other half to a homodyne detector that you program to measure along this axis, and yeah, lo and behold, you have a signal going in and you get a value for Q and a value for P at the outputs. This seems like a contradiction, but then you remember that when you split your light in two, that there is a little bit of vacuum coming in, and vacuum does not have energy, but it has field fluctuations, and when you measure fields, these fluctuations will show up, and so what we get is essentially additional noise on these two measurements. So when you do something like this, what you end up doing is a noisy measurement of both field quadratures simultaneously. And this seems kind of practical and experimental, but this is actually also related to what you call the Husimi Q function. So the Q function is a probability distribution on your phase space, and it is exactly the probability distribution that describes these measurement outcomes. So you have these points Q and P that you jointly sample. You sample them according to some probability distribution, and this is exactly the Husimi Q function of your the state, the quantum state that describes your initial light. And this is interesting because these Houdini functions, in principle, are a complete description of your quantum state. And so I hope with this slide that I gave you kind of an idea of the kind of observables that we are interested in, the kind of measurements that we do, and the kind of phase-based descriptions of light that we are interested in theory. So I told you what we measure. I've not told you why we measure it. So we hope someday, one day, maybe to build a quantum computer like everyone. Maybe not us in our experiments, but this is kind of one of the main motivations. And so you have probably seen that there are these kind of claims that have come out recently that people have achieved a quantum computational advantage using photons, so basically Gaussian boson sampling for the people who know what that is. And of course, in meantime, this I think people have simulated it now on a normal laptop in a matter of a few seconds. So it's classical algorithms have caught up again. But so it's this kind of implementations that I want to focus on in my talk, because these are all incarnations of what you could call more generally sampling problems. So what is a sampling problem? You could kind of very generally describe it as a setting where you have a bunch of input states that you create in your, basically as an optician you would say, the kind of state that you can easily get out of your source. So you have them in many different modes. Then you are going to do a bunch of quantum operations on them. This can be more or less anything, but the main idea is that you would want to create some kind of entanglement between all of these different modes. And then at the end, you want to perform some measurements on them. So in my talk, I'm going to make these things very kind of general and arbitrary. I'm going to take all of this, and I say this is just some large multimode state row that I assume that you can make in your experiment. And then the measurements, I'm going to assume that you do single mode measurements and that they are projective. You can relax these assumptions if you want, but it makes things a bit easier to explain. And so when you now want to describe the probability to get a specific measurement outcome associated with all these projectors, you basically do this. So you take the trace, the density matrix, and the projectors. You all know this. And so the kind of questions that you're interested in when you're now studying these sampling problems is basically understanding when it is difficult for a classical computer to simulate such a setup, to basically sample these measurement outcomes given a certain state. And so we want to understand when this is hard and when this is easy to do, and then you can go into a whole kind of zoo of different possibilities of types of simulations. You could try to explicitly calculate these probabilities. You can try to do some kind of effective sampling. And here I'm going to focus on the case where you want to kind of try to see how hard it is to really calculate these probabilities. And so I'm a physicist, so from a physics point of view, the questions that you then ask are, what are the physical resources that you would have to put in to make this hard to simulate? And so my overview of my talk is essentially a big spoiler because I'm just going to tell you what you need. So on the one hand, the first part will be about the resource high stellar rank that you need. Probably you don't know what that is. Don't panic, I will explain. And then the second part is about the fact that you need some non-Gaussian notion of entanglement. You probably also don't really know what that is. Don't panic, I will also explain if there is time. So, okay, so first of all, high stellar rank. So the tool that we use here is something known as a stellar rank, which my coworker Ulysse defined in his PhD thesis, and it is based on these Houdini Q functions, which is also one of the reasons why I introduced it before. And so when you look at these Houdini Q functions, the things that you measure when you do heterodyne double homodyne detection, you notice that if you look at these things from a theory point of view for pure states, that actually they will either be Gaussian probability distributions or they will be probability distributions that have a very weird property, which is that they will touch zero in a countable number of points. So this may be a finite or an infinite number of points, but it's always discrete. And so what Ulysse defined as a stellar rank is nothing more than essentially the number of zeros of this Q function. And then you divide it by 2 because apparently it's always an even number. There are more fundamental reasons for this, but for this talk you can just remember that it's essentially the number of zeros of the Q function. And then you reach a problem because when you try to extend this definition to mixed states, you find that actually these zeros disappear more or less immediately, so this is not a good definition. And so then for mixed states you can do this kind of convex roof construction where you, if you don't really know what that is, the idea is essentially that you are going to look at what is the maximum stellar rank pure state that I need to produce this mixed state. And so that is then what you define as the stellar rank of the mixed state. And so now I'm going to skip more or less directly to some of the main results that we obtained. So what we developed in our work is a connection between, so we are back to our sampling problem. We have a state upon which we perform measurements, and so we found that the probability to get this measurement outcome here, which is kind of very generically defined, that you can always connect this to some more like probability or probability density in this case for this more concrete sampling setup. So here the alphas, I realize I didn't write this down. So this would be projections on coherent states, which are again what you do when you do this double homodyne measurement. So you get these projections on coherent states. Here we still have the state that we have here, but then we have these auxiliary or additional photons that you have to put in. And the number of photons that you have to put in is exactly given by the sum of the stellar ranks of all of these states that you are projecting on here. So, and then finally you do some big Gaussian transformation to connect all of these input states to these coherent states upon which you project. So to give you a bit of an idea of what these Gaussian transformations are, you have a bunch of single mode squeezing operations in there that are not particularly interesting perhaps, and then what is more fun is that you get these kind of two mode squeezing operations, which will be essentially gates that are going to connect these auxiliary photons here to your initial state. And there are also a bunch of displacement operations that are also perhaps less interesting. So you get this kind of connection of this kind of generic sampling protocol to something that is much more concrete, and you can always build this. But it's the subtlety, and that is what I will come to now, is that it is really like a probability per probability kind of mapping. So the circuit that you get here and the number of auxiliary photons that you get here will actually depend on the measurement outcome that you are considering. So for every measurement outcome you would have to do a different little mapping. But so when I talk about connections, dualities and so on, what I really mean is that you can write this probability in terms of this identity, where this is basically the probability density, you could say, to get this measurement outcome for your coherent state projections. But then you see that there is a bunch of, there are many subtleties that are hidden. So here you have these psi that pop up, that you divide by, and these are the two-mode squeezing parameters, two-mode squeezing strengths that we have in this Gaussian transformation. And then you see that it's not actually an exact equality. We add a plus order epsilon here, which is what you do when you do quantum information stuff and you do things that are perhaps not completely exact. So then, I mean, from a physicist's point of view, when you look at things, so this identity would become, this would become exact in a limit where the two-mode squeezing goes to 0. And then, of course, as a physicist, you say, well, it's never exactly 0, but when you talk to experimentalists, they say, no matter what kind of state you have, we can always find something where it's effectively more or less giving the same thing as when it were 0. They don't really like it, and you have to make things rigorous. So this epsilon, basically just to say, and you can read the paper if you're interested, we essentially show that there is really kind of a nice and clean way of exactly controlling the errors that you make when you do this kind of identity for finite squeezing. So you tell me what the error is that you want to allow me to make, and I will tell you how much squeezing you have to put there. Okay, so perhaps then what does this mean? So why is it useful to have such an identity? Well, in general, it's very difficult to come up with algorithms to calculate these probabilities or to simulate these things, but it's much more easy to come up with, with algorithms to calculate these much more concrete probabilities. And so this is what we did. So we did something called strong simulation. Strong simulation is a fancy way of saying that you just calculate all the probabilities brute force. And so, well, I'm going to give you the result for pure states because it's a bit easier to formulate, but you can do the same thing for mixed states. So this is our identity that we have, and we are going to use some observational facts. You could say that if any kind of bosonic pure state that you have, you can always approximate it by a state that is of the form where you have a Gaussian transformation and a core state. And so now you tell me I don't know what a core state is, so I will explain you. So a core state is essentially a superposition of Fock states, so photon number states, but with a finite number of photons. So this is kind of the important thing here, is that we put in our superposition, we put an upper bound on the total number of photons, and this upper bound is exactly, again, the stellar rank. So this would be the stellar rank of the core state, and the stellar rank does not change under Gaussian transformation, so it's also the stellar rank of psi. So now we inject these two ideas together. So this would be now the state that we are injecting into our system. We use an earlier result of Ulysse where he showed that if you have a core state and a Gaussian transformation and you project on coherent states, then you have an algorithm based on Hafnians to calculate these probabilities. So, well, this C is a core state. When you add some Fock states to it, or some single photons, this remains a core state, so we can just apply this now to this circuit that we found. And what you find as a result is actually that the computational cost of calculating these probabilities and of doing a strong simulation of your sampling protocol, that this scales exponentially with the total stellar rank of the full system. So the stellar rank of the state plus the stellar ranks of all the states that you are projecting on in your measurement. And so this is a way, of course this is an algorithm. Sometimes you may find easier algorithms to calculate these probabilities and so on. But what this shows you is that you need to have a stellar rank that is sufficiently high, because if you don't have that, I can simulate your protocol. To me, this was a very depressing result in a way, because I always hoped that getting a high stellar rank means having effectively many photons that are really actively participating in your computational process, and this is usually very hard to get experimentally. I always hoped that there would be some way of getting around this by doing kind of exotic things with modes and so on, but this turns out to be not the case. So, but yeah, so it's a new resource that we identified. So I guess I have to speed up a little bit looking at the time. So I want to now come to the second resource that we identified, which is non-Gaussian entanglement. So as I said before, we found a way of calculating probabilities of getting measurement outcomes here that always works. You do the mapping, you do this kind of brute force calculation, and you know what the complexity is of the brute force calculation. But then you can try to be clever, because in some cases you maybe have some properties of this circuit that you can exploit to make it easier to calculate without having to brute force things. So the next question you ask is, well, when are these probabilities perhaps particularly easy to calculate? And so there we came to an observation that actually it's interesting that here we do projectors on coherent states, and coherent states have very nice properties. They transform very nicely under passive linear optics operations. So basically interferometers, beam splitters, phase shifters, and so on. And what this means is that you can implement these operations in a way in post-processing. Said differently, if this is a passive linear optics device, calculating this circuit is exactly as, well, or more or less as hard as calculating this circuit. So this means that if all the entanglement that you have here in your row total is just generated by passive linear optics, by interferometers, that actually you can simply undo it, and you can simulate some or calculate a much easier probability, do a very simple transformation on it then at the end, and you are done. So, so from a physics point of view, this means that in this row total here, you need to have a kind of entanglement that you cannot undo with passive linear optics. Okay, thank you. So you cannot undo it with passive linear optics, and so this is a manifestly non-Gaussian type of entanglement, because any Gaussian state that you have, you give it to me and I will tell you what the linear optics transformation is that you have to do to transform it into a separable state. And so this got us to kind of more physicsy topic of studying this kind of non-Gaussian entanglement. So you can see this a bit differently in the sense that a kind of boiled down version of this is if you give me the covariance matrix of row total, I can always find a transformation to do on this covariance matrix that will transform it in the covariance matrix of a Gaussian state that is separable. And so if I do this operation and then in this basis I see that there is still some entanglement present in the pure state, I can say that I really have a very non-Gaussian sense of entanglement. And this is very hard to see experimentally, because when you talk to experimentalists, they really like to base all of their entanglement witnesses on covariance matrices. So this will not work. So the question that we have here, and there is something wrong with this sentence, I think, but so the question that we have here is that, like, how can you detect this kind of non-Gaussian entanglement experimentally? And very often in quantum optics, when you do things that are Gaussian, it's kind of easy, and once you go to things that are non-Gaussian, it becomes utterly impossible. And you have the same problem here, like the brute force solution that you could have is to say, I do a full quantum state tomography. And then you reconstruct the full density matrix, you know everything there is to know. You can do something like you do the partial transpose, you test the PPT criterion, and you have a nice and calculable entanglement witness. The problem is that full quantum tomography is extremely expensive, so people have done this while making a bunch of assumptions on their state to make it much more easy, but in general this is very costly. So we tried to see in a simple two-mode case whether we could find much simpler techniques to use. So we looked a little bit at metrological witnesses. I'm not going to say much about this, but the idea is that you are going to have Alice and Bob, who both implement a parameter on their side of the system. They're going to together try to estimate these parameters, and if they can get an estimation precision that is higher than what you could possibly get with separable states, you know that you have entanglement. And here we could show that actually with using homodyne measurements and only 2 measurement settings, that you can already get good entanglement witnesses, but they are extremely sensitive to loss for the type of states that we are interested in. So from an experimental point of view, like we have entanglement witnesses that are somehow easy to implement, but the problem is that they do not work. But then the upside, like the positive side, is that here you only need 2 measurement settings and here you need infinitely many. So we have one something, and so the question is, can we now kind of get the best of both worlds and use this kind of data to get this kind of information? And the way we do this is by asking basically a computer to do it for us and to train machine learning algorithms. And so the idea here is that we found a good way of generating density matrices that look like the type of states that we have experimentally. We do this, from these density matrices we can check, for example, the PPT criterion, see whether there is entanglement, and then we can generate also these kind of homodyne data. So this is, you have 4 settings, so you can measure, well, X and Q are kind of interchangeable here in this talk apparently. So you can do, you can measure QQ, you can measure QP, PQ, and PP. So you have, these are each detector has 2 settings, so 4 in total. You get 4 histograms. And you see already that for some of these histograms it looks kind of boring and some look much more interesting. And so you can ask now if you know for every kind of state that you generate that corresponds to these histograms whether it was entangled or not. So you can wonder whether if I just kind of do some kind of clustering algorithm to look just at how similar different histograms or sets of histograms are, can I see that entangled states and non-entangled states are clustering together? And so this is what you do. So we do some kind of data visualization algorithm, and you see that you have these nice clusters that appear. You see a lot of structure, but the bad news is that the good news is that there are some regions where there are only entangled states. The bad news is that all of the separable states are somehow intertwined between some other entangled states. So this shows you that there is some structure, but that we cannot really see it immediately. And so we asked a neural network to look for this structure for us. And so what you see here then in this plot would correspond to the information that you feed in to the neural network. What you ultimately want to get out is just an entanglement label. So this is a network that will tell you, do I have entanglement or not? What is very interesting for us was actually that we found that at some point we learned a lot from not looking at the labels that the network spit out, but actually at the layer before. I don't know whether you see it really with the color, so there is a little layer written there as well. And if you do this, you see something like this. So you after a few layers of neural network, you essentially filtered out all the separable states or all the positive partial transpose states, and you see that these groups appear. So this is nice because it shows you that the neural network does what it is supposed to do. But then you look at this a bit more and you start to see a lot of additional things, because you see here in your entangled states that there are many different clusters sitting around. So here you have like a blob where you could ask, does this blob have perhaps a different kind of entanglement in it than the blob that is sitting here? I don't know. So this is the kind of questions that we are now exploring. We found out that this is a nice technique of looking for additional structures in your entanglement or other structures in your states. The final thing that is nice is if you have a type of data that you feed in that look nothing like the data you used for training, you will see that they actually will fall somewhere completely outside of this plot. And if you do this with your experimental data and you get this as an output, you should be worried and you should say that perhaps you should not trust what the network is telling you. So now I have a slide which is essentially just on showing you that it all works. I'm going to skip this because I think we're more or less, the time is more or less over. So my take-home message is that you need a high cell rank for reaching a quantum computational advantage in optics, and you need non-Gaussian entanglement or some notion of it. I also showed you that this non-Gaussian entanglement can be detected using these neural network techniques. And because Alexia asked to have open questions, I want to end with one big open question that I have as a long-term outlook, which is that, so I talked a bit about the fact that you need non-Gaussian entanglement and stellar rank for a quantum computational advantage. There is an older work by the group of Jens Eisert, where they show that you need Wigner negativity. This has been generalized to other types of quasi-probabilities and so on. We did some work showing that you have a connection between quantum steering and Wigner negativity. There is some recent work showing that there is really a fundamental connection between contextuality and negativity of the Wigner function in the continuous variable regime. And I think it's a very interesting question to wonder how all of these different things are somehow connected together. And to wonder whether is there kind of one source that you can use as like the fuel of, let's say, maybe photonic or continuous variable quantum computer. And I think this is a very important question also for the people here, because in the sense of the quantum energy initiative, this would be the thing that we have to make if we want to build a quantum computer. And so this would be the thing that we want to generate as efficiently or resource efficiently as possible. And I think as long as we've not really found an answer to this question, things might be quite difficult. So I think if we find an answer here, there is a lot that we can do. So and with that, I thank you for your attention.
Okay, can you hear me?
Yes, I
Yes,
can hear you.
great. Right, very nice work, very interesting.
Thank you.
On the non-Gaussian entanglement, you mentioned the PPT criterion, but this is not a necessary and sufficient criterion for non-Gaussian states, and so I wonder whether you use any other witnesses of entanglement.
That is a good question. So actually, when I can go back to the slide, and so you see here that when I show you the last layer, there are actually 3 labels.
Mm-hmm.
And the 3 labels actually correspond to 3 different entanglement witnesses. So I
Ah.
talk about the PPT criterion because it's the simplest, but
Yes.
we do these kind of quantum Fisher information-based entanglement witnesses as well. So yeah, and in principle, any witness that you can calculate, you could put it in there and you can do the same algorithm. So we tried for 3 different ones.
But then you
but
catch a
could
lot
do-
more, so this is very good.
Yeah. And
You
so
catch
what's
a lot more.
perhaps interesting is that for these kind of machine learning approaches, people have found that if you train these networks for different properties at the same time, that sometimes you can get much more structure in your data. So putting different witnesses there might actually be something that could teach you much more about entanglement structure than just whether there is entanglement or not.
Yeah, okay, perfect, thank you.
Hello, thanks for the great talk. I'm curious regarding stellar rank. As you know, it looks like a resource for advantaged quantum computation. I'm curious if it has ever been cast in the formal framework of quantum resource theories in terms of free operations, free states.
It's a good question. It's not the first time I get this question, and so I'm happy to tell you that actually we have a big European project where one of the parts, and this is more my colleagues that will work on this, but this is exactly what they want to do, build a resource theory for stellar rank, or even a multi-resource theory for stellar rank and non-Gaussian entanglement. So yes, there is that is being worked on, but so there is a whole formalization of the concept of stellar rank, but of how you use it in a resource theory sense, this is still kind of out in the open.
Right, so this is Damien Markham and
Damien is not involved in this,
okay.
but so it's Ulysse who is now a permanent and who is pushing these things.
Excellent.
Yeah.
I have one second question, if you don't mind, which is obviously we need thermal non-equilibrium for stellar rank.
Obviously we need?
Thermal non-equilibrium, given it is a non-Gaussian type state. Is there any formal relations between, given this is an energy workshop, between sort of the free energy or of the stellar rank states, or some sort of relation between stellar rank and the free energy they must have to achieve a certain stellar rank?
That's a really deep question. So I will just simply tell you that I don't know, and that one of the reasons for me to come here to this workshop is that I hope to learn, to find ways of answering this kind of questions. So.
Maybe we can discuss sometime. Thanks.
Thank you for the presentation. It was very interesting. Just for the high stellar rank, I have a question. So you say that it's so the cost of simulating grows exponentially with the stellar rank. But my question is it like you map? Probably you explained it, but you map it to a problem that is known to be hard, such that you have this result, or because often, like to show that a computation is hard, it's related to a problem that is under complexity conjecture. So how does this work?
Yes, so I tried to emphasize it, but maybe I did not do this enough. So the point is that we show that the high stellar rank is a necessary resource, but not necessarily a sufficient one. So what this means is that you can, like, we find an explicit algorithm to do these kind of simulations based on the stellar rank. And so this algorithm is related to calculating Hafnians, and you know that calculating Hafnians is in sharp P, so there is, I guess there is no real way around, and there is probably no much simpler way of doing things in a way that makes these stellar ranks become like appear. Then, like, it could be that there are ways that are completely different, that if you have some specific sampling problem, that actually the real, like, that there is a much simpler way to calculate all of these techniques. So in this sense, there is no, you don't map it to some, there is no statement that if I could simulate this, with this algorithm, that then it would mean that, like, the polynomial hierarchy breaks down or something like this. So.
Okay, thank you.
Thank you, Mattia, for the nice talk. I was just having a small question on the C and the G transformation.
Yes.
I don't get how you can get like a coherent state if you start with only, which has a stellar rank of 0, only starting with 0 Fock state, like with vacuum. Is it
how you could get a coherent state, you asked?
Yeah.
But this is because this is all included in your Gaussian unitary transformation.
Okay, so it's not a linear
you really
interferometer.
you could see this as you could minimize over all the possible Gaussian unitaries, and then at some point you will find this kind of finite superposition Fock state that is left, and that will then give you the stellar rank.
Okay,
So.
thanks.
Right.